Welcome to the presentation of Reduce and Reconstruct, ASR for Low-Resource Phonetic Languages. I am Anuj Diwan. I recently completed my undergraduate computer science degree from the Indian Institute of Technology, Bombay. My co-author is Professor Preethi Jyothi, my advisor at IIT Bombay. RNR is a seemingly simple but effective technique to improve end-to-end speech recognition for low-resource phonetic languages. End-to-end is always an attractive choice since speech is mapped directly to graphemes or subwords derived from graphemes. However, it is also very data-intensive and tends to underperform on low-resource languages. In our approach, we train two modules: a speech recognition system with a linguistically motivated reduced alphabet. For the speech recognition model, since the alphabet is smaller, it is easier to learn and it is less data intensive. This is the reduced step. Then we train an FST-based reconstructor that recovers sequences in the original alphabet. This is the reconstruction. We run experiments on two Indian languages, Gujarati and Telugu. With access to only 10 hours of speech, we obtain relative WER reductions of up to 7%. The first step in our approach is to devise a reduced vocabulary that merges acoustically confusable and linguistically discriminative graphemes. This is an example of such a reduction for the graphemes k, kh, g, and gh, all merged into the same grapheme. The same example is there for Telugu and also represented as IPA. Then, given labeled speech data, we transform transcriptions using this reduction. And then we train an ASR system to map the original speech to these reduced transcriptions. So, for example, a sound wave saying bhasha would be mapped by the speech recognition system to the sequence persa. Finally, we train a reconstructor to reconstruct the original grapheme sequence, such as bhasha in this example, from the reduced grapheme sequence persa. In our FST-based reconstructor, the input, that is the reduced grapheme hypothesis from the speech recognition, is represented as a linear acceptor H. So, for example, persa would be represented as simply a three-state FST with the arcs per and so. Then we compose it with the reduction FST S. So S makes use of the reduction mapping. It is a single state FST. It takes reduced graphemes as input and produces the original graphemes as the output. So for example, if the reduction was k, kh, g, and g being all reduced to k, then the reduction FST would be represented like this. K would be able to go to k, also would be able to go to k, also would be able to go to g, and also would be able to go to g. And so, if one obtained the reduced grapheme k, then S would be able to transcribe it to any one of these four original graphemes. Then we compose it with the edit distance FST E. E is an FST that takes a grapheme sequence as input and it produces all the grapheme sequences that satisfy the constraint that every word in the output is within an edit distance of D from each word in the input. This gives some leeway to modify the input. The allowable edits are substitutions, insertions, and deletions. Each edit incurs an additive cost lambda to dissuade too many edits. Now, D and lambda are hyperparameters in our approach. and are tuned on the speech recognition dev set. This E was inspired by the fact that many speech recognition errors were caused because the prediction was only a few characters away from the ground truth. Then we compose it with the dictionary FSTL. We first fix a vocabulary, in this case the set of all training set words, and it simply maps a sequence of graphemes to a sequence of words. Such as if one had the sequence of graphemes bh followed by a followed by sh followed by a, then it would map it to the word bhasha. And out of vocabulary words are mapped to a special unknown word. Finally, we compose it with the language model FST-G. G is an n-gram language model trained on the speech recognition training set transcriptions. H composed with S, composed with E, composed with L contains all the possible reconstructions. Composing this with G rescores the reconstructions, giving higher scores to meaningful sentences. Finally, we obtain the output O, the best reconstructed sequence, by running the shortest path FST algorithm on the composed FST HSELG. O is the final prediction. These operations are efficient due to highly optimized FST libraries. We run experiments for Gujarati and Telugu. Our speech recognition architecture is the bidirectional LSTM. We run experiments both without and with an RNN-LM. We test with we run experiments for two training durations, the full and 10-hour subset of the training set. And we also run additional 10-hour Gujarati experiments on the advanced conformer architecture. This is the bidirectional LSTM architecture, where we use a forward and a backward LSTM to convert the acoustic features to symbols. We use the ESPNet toolkit to train hybrid CTC attention by LSTM. These are some of the major hyperparameters that we use. The FSTs were implemented using the OpenFST toolkit. The LM FST-G is a 4-gram language model with laser-nade discounting implemented using SRI LM. And by tuning D and lambda on the dev set, we get the best tuned values as D equal to 3 and lambda equal to 5. These are the pre-reconstruction speech recognition results. We run experiments for both full and 10-hour training durations. Identity is the baseline with no reduction. Row 1 is our linguistically motivated reduction, and row 1 rand is a reduction of the same size as row 1, but it is randomized. That is, the graphemes that are being merged are random. These are reduced word error rates, RWERs. We call these RWERs because the predicted speech recognition hypothesis is in the reduced alphabet, and the grapheme sequence that it is being compared against is also the reduced ground truth text, not the original ground truth text. So as one can see, the RWERs are lower for row 1 than the baseline, both in full and 10R. This shows that the reduction fundamentally simplifies the speech recognition task. And comparing the RWERs for row 1 and row 1 rand, one can see that since row 1 rand has a higher WER, the speech recognition task is not simplified in the case of the randomized reduction, which shows that a principled reduction is important. Just some reduction is not sufficient. Now, after passing the hypothesis from the speech recognition systems through the reconstructor, we have post-reconstruction results. These are actual word error rates computed between the final prediction and the original ground truth. These are results for full and 10R on different settings of D and lambda. As you recall, D equal to 3 and lambda equal to 5 were the best values obtained. The baseline is the identity system without any reconstruction. One can observe that even for exact reconstruction, that is D equal to 0, no edits are being allowed here. For exact reconstruction, reduction outperforms both the identity after reconstruction and the baseline, which is identity without reconstruction, both in full and 10R. And increasing D improves all the WERs as expected because it makes a more powerful reconstructor, but reduction still outperforms the other two. And improvements are more pronounced in the low resource 10R setting. The decrease is much larger in this setting than the full setting, although there are decreases in both settings. Now we'll turn to the experiments of Bialystium with the RNN-LM. The RNN-LM was trained on transcriptions of the full speech data. These are the results with the RNN-LM using the best D equal to 3 and lambda equal to 5. Here we can see that these baselines are with RNN-LM is better than the baseline without the RNN-LM as expected. The reduction significantly outperforms the identity in the 10R setting, and it also outperforms the identity in full for Telugu, but it does not do as well in the full setting for Gujarati. Now we turn to the conformer experiments. This is the conformer architecture. It is a convolution augmented transformer used for speech recognition. We use the ESPNet toolkit to train conformers as well. These follow similar trends as for the other experiments. You can see that the test WER has improved for row 1 as compared to identity in both settings. Note that here lambda equal to 10 was obtained as the optimum hyperparameter as opposed to lambda equal to 5 in the previous experiments. Here are a few analyses and discussions. We show in the paper that our reduction is superior to randomized or even less compressive reductions. We show that the reduction function corrects 16.29% and 16.92% errors, substitution errors caused by the identity system, and the reduction function decreases LM perplexity. So if you train an LM on the reduced text, then the perplexity on the reduced test set is less, which shows that the ambiguity decreases. And a larger drop for Telugu corresponds to larger improvements observed for Telugu in the speech recognition experiments we saw earlier. These are a few qualitative examples. R is the ground truth. I is the prediction made by the identity system, and row 1 is the prediction made by our reduction system. One can see that no and mo, which are in the same reduction category, the identity system incorrectly predicts mo because and mo and no are acoustically confusable, whereas our reduced system is able to predict it correctly. The same happens in the confusability between the and the. This is a Telugu example. Here the ground truth contains the long E character, which is predicted incorrectly as the short E in the identity system, but correctly as the long E in the reduced in R reduction. As future work, we plan to automatically learn a data-driven reduction mapping, train more powerful sequence-to-sequence reconstructors, combine two modules that we saw into a single module using a bottleneck layer and multitask learning, and instead of passing the one best hypothesis from the speech recognition system to the reconstructor, use the decoding lattice and pass that to the reconstructor to get a more powerful reconstruction. In conclusion, we propose a simple reduce and reconstruct technique and demonstrate its utility for two Indian languages. And we show that as the training data decreases, our approach yields greater benefits, making it well suited for low resource languages. Thank you.